Do we have, so can you put it on, right? Very good. Now we see that, I mean, now I see it very well. So I think now we have Jeremy Quastel from University of Toronto, and he will speak about the KPZ fixed point. Thank you very much.
Okay, so hi everybody, and thanks for the invitation. This is a kind of general talk to describe the KPZ fixed point, and I hope everybody will ask questions. It's hard to say everything in 1 hour. So this picture this is actually from a physics paper. It's a real thing. It's a Eden model, off-lattice Eden model, where balls are being added to the cluster as long as they're neighbors. And neighbors here, I actually don't even know the definition because it was really from an experimental physics paper. And they're being added at rate 1. And so you can see the infected individuals are pink, and they're being added to the cluster. And the question is to describe the universal laws at the boundary of such a thing. And what's not too hard to see is that the boundary, and you can you can look in any direction, but I decided to look in this direction because over this direction it really does, at least near this arrow, look a bit like a function. And so this is what I'll call the height function, h. And I guess it's kind of clear that the thing's growing at rate some constant times t. And this kind of constants are very non-universal. And the universal thing that we want to see are the fluctuations around this this deterministic CT growth. And they're at this strange scale t to the 1/3. And then there are these universal processes which govern the lateral fluctuations, which here I've called A. A is for Airy process, because this thing started with a seed, and so this will be a thing called the Airy process. And it lives on a scale of t to the 2/3, and x here is the lateral variable. Okay, so this is the kind of thing we want to see, and this Airy process is a special stochastic process. It's a very non-trivial process. They look locally like Brownian motion, and they're given in terms of their finite dimensional distributions, which are given by certain determinants. And so that's what we want to kind of understand in this talk. And they depend on the initial data. So if you started this Eden growth with a half space instead of with a seed, so here you can see you start with a seed, and the thing, because actually this thing is spherically symmetric because it's not on a lattice. So it'll actually be a ball in a large time. But if you start with a half space, you would just have a half space moving along, and you would see roughly the same thing, CT plus t to the 1/3, but there would be a different Airy process, which would remember the flat initial conditions and would be given by certain other Fredholm determinants. Okay, so that's what we want to try to explain here. Of course, one of the problems with this picture here is that it's not really, the h is not really a function. You can see there's overhangs, at least if you go a little bit to the side. And that makes life difficult. And so one wants models which are directed. Oh, okay. So I just wanted to mention that the phenomenon is extremely general. And though it can't be proved in any of these cases yet, it's true, for example, if you took a random Riemannian metric and looked at the balls in that Riemannian metric, the ball of size CT would have these little fluctuations on top of size t to the 1/3, and it should be, in principle, it's a nice theorem for somebody to try to prove someday, this same process A of x living on this scale t to the 2/3. And I'll explain what A of x is later. Okay, so we want to look at directed models, and the most famous of these directed models, and the first model studied, back in the 80s is this model called ballistic aggregation. So the ballistic aggregate is a Markov process with state space piles of blocks over Z. And the way it evolves is that blocks are falling at each site independently as Poisson processes. And the blocks just pile up, except for the one little twist that a block can stick to the side of the next tower of blocks. As you can see here, this block is falling and it doesn't just pile up over the one block below it, but it actually sticks to the side of the next block. And so this stickiness is what causes the outward growth, and it's that nonlinear thing which makes the thing interesting. Okay, again, we're in a world here, this is just the thing on a big scale. We're in a world where nothing can be proved. And one of the reasons nothing can be proved about this ballistic aggregation model is that nobody knows. So now it's a height function. Now it's a genuine height function. So this is the evolution of a function h of x and z. Markovian evolution, easy to describe, except that nobody knows what its invariant measure is. It's expected that the invariant measure somehow looks like a Brownian motion on large enough scales, but that's not known. Okay, so that's a big problem and related to what other people are talking about here. Okay, so now we'll move to the physicist's famous model of ballistic aggregation, which is the Carter-Percy-Zhang equation. So KPZ, and so we're in D equals 1, KPZ, is a model for what we were just talking about. Now the height function is over the continuum. So it's a function of h, of t, and x is a continuous variable. It's a Markov process, and the stochastic evolution is sort of defined by this stochastic partial differential equation. And so there's three basic mechanisms pushing up this height function h. So starting from the left, the first thing is the forcing. So this thing's being pushed by a space-time white noise, and you can just think of the h being kicked randomly at every space-time point independently. Of course, the space-time white noise isn't a function, but let's not worry about that right here. And so that corresponds to the Poisson arrivals independently at each site of the ballistic aggregate. And then there's another term, the relaxation term, which is, as you can imagine, put in there to keep the interface as an interface. So it's a somewhat smoothing term, but the balance between the space-time white noise and the smoothing term is, of course, very delicate. Even if you didn't have the nonlinear term, you would see this as the linear stochastic heat equation, and you know that this thing has a Brownian invariant measure. And then the most important term is this lateral growth term. So the lateral growth term is because the growth, and you can see in this little picture here, the growth is outward. So the growth is not just up, but outward because of the stickiness of the particles. And whenever you have an outward growth like this, the vertical component of the growth, which should be dth, is a nonlinear function of the slope. What nonlinear function? Well, okay, if you look at the little picture, you could do a careful calculation. You find out it was the square root of 1 plus dxh squared. But the idea is that the actual nonlinear function here doesn't matter very much. And if you had some funny nonlinear function f of dxh, you could expand it as a Taylor series. And the first term, which is just a constant, you could remove by a height shift. The second term, which would be f prime of times dxh, you could remove by a lateral shift. And then the first term that you can't remove by a sort of simple mechanism is the quadratic term, And so you leave it in there, and that produced this magic equation, KPZ. Okay, so KPZ is better than ballistic aggregation, partly because we actually do know its invariant measures, which are Brownian motions. So two-sided Brownian motion is invariant for this process, and you can think of this as a kind of evolution, a very non-trivial evolution of Brownian motions. Or if you start with, say, some deterministic initial data, and you snap your fingers, it'll immediately look like a Brownian version of your initial data. And because it's locally a Brownian motion, always through the evolution for any positive time, of course, the dxh squared term makes no sense. And so really this thing needs a kind of infinite renormalization. And well, I think everybody knows the story that Martin Herrer made sense of that. And so this equation is definitely well posed for up to a finite time. Okay, but we're interested not in things like that. And in fact, the well-posedness isn't quite necessary for us anyway, because you could just define H to be the log of the stochastic heat equation, which was already known to be well-posed. We're interested in the large space-time scales. Oh, okay, here's the video. Let's see. Can you see this video playing? Okay, so this is fluff burning in a park in Madrid, I think. And you can see very, very well the KPZ front. Just to show you how general these things are. I was actually just happened to be watching the Weather Channel and saw this and took a quick movie of it. Okay. So we're interested in the large time behavior of this thing. So as you can see from the fluff burning, there's a constant times t, this thing growing. And as you probably couldn't see from the picture, the fluctuations are of size t to the 1/3, again, times some process A. And here A, I didn't write the variable in, but it's a lateral stochastic process. So this A is supposed to govern this sort of height function here. That thing rescaled is supposed to be the A of x. That's the stochastic process of the front we're interested in. And it lives on a scale t to the 2/3. So that should say A of t to the minus 2/3 times x. And here you have a different area process, because you can see from the picture that this thing started out with a flat interface. Okay. To see these stochastic processes, we should just do a rescaling. Instead of calling it t, we should have a variable epsilon, which is our ratio of micro to macro. So we're looking for small epsilon, which means to zoom way out. And so we look at these scales, and of course, what's written here, this rescaling is exactly the same thing as saying that the fluctuations are of size t to the 1/3. So t here is epsilon to the minus 3/2. So the fluctuations are of size epsilon to the minus 1/2. And so they have to be scaled down by epsilon to the 1/2 to see something. And the lateral scale is epsilon to the minus 1, which is time to the 2/3. So this is saying exactly the same thing. And so what one expects in all models in the KPZ universality class, and in fact, this is essentially the definition of the KPZ universality class, is that there's an analog of the height function. It could be a free energy or something like that, which under this scaling, this is the KPZ 1, 2, 3 scaling, after subtraction of some very large constant, C epsilon t, you could see here that under this scale, C epsilon would have to be something like epsilon to the minus 1. You should see universal fluctuations, and these fluctuations I'm going to describe in the rest of the talk. Okay. Good. So here's the kind of result which we get. And the results are, I must say, rather unexpected. Okay, so I'm just going to describe the result first for the flat initial data. And in terms of the asymptotic one-point distribution function. So I've done the rescaling, which I described, the 1, 2, 3 scaling on the height function of KPZ. As I said, it started with flat initial data, which just means to start H0 equals 0. And now we look at the probability distribution function, f of r. It's a function of t as well. It's not a function of x because we started with flat initial data. And for flat initial data, there's no dependence on x because statistically it's the same everywhere. So it's a function of f of t and r. And r is just the probability distribution function variable. So the result is that if you take this function, f of t and r, and differentiate its log twice, this function called phi satisfies the Korteweg-de Vries equation, KdV, the famous integrable nonlinear PDE. Okay, so you could stare at that for a minute and wonder how such a thing could be true. If there's no questions, I'll go on to the more general version. The more general version will be what happens if you don't start with flat initial data, you start with some other initial data. So now we're starting with some general initial data. Of course, it has to have this diffusive rescaling, which is the non-time part of the 1, 2, 3 scaling. So I'm starting with a function h0x. And I do the same rescaling, the 1, 2, 3 scaling. And now my distribution function depends on t and x. And of course, the distribution function variable r. So that's the asymptotic probability distributions, starting with an initial interface, which is on a large scale, this h0x. And this one, the second log derivative, satisfies this famous two-dimensional version of the KdV equation, Kp. So I've written the Kp equation. Again, it's a nonlinear integrable partial differential equation. So you could stare at this thing and you can wonder how such a thing can be true. And I'll leave it up here for a second because you could stare at it for quite a while and wonder how such a thing could be true. And I've been staring at this thing now for about 3 years. And I don't have too much more idea after 3 years why it's true than when I started. It can be proved, and I'll try to explain to you the proof, but it's not something intuitive. Okay, so now even more generally, we'd like to know what the n-dimensional distributions are of this limiting fluctuation fields. Sorry, oh, there it goes. Okay. So again, we're starting with general initial data, h0x. H0 can be a very, very general function. It only has to be lower semi-continuous. And now I look at the n-dimensional distributions. So I'm looking at the height function in the macro rescale time, but now at a bunch of space points, x1 through xn. And so I have an n-dimensional probability distribution depending on time and x1 through xn. And the theorem says that now the first log derivative, it's really actually the same kind of equation about the second log derivative, but it's written in a slightly different way. So what we're saying is that the first log derivative is the trace of a matrix capital Q, whose derivative little q, so little q is playing the same role as the phi in the previous equations. And they satisfy a matrix version of the KP equation. So I don't think it's worth staring at this equation too hard, except that you can see that it's a matrix generalization of the KP equation if you look. Interestingly, in the variables, T and the sum of the R's and the sum of the X's. Okay. So I'll just leave this up for a second so you can appreciate it. And then I'll try to comment about all these results. Okay. So here's the KP equation, the one-dimensional version at the top. And the question is why this happens. And the answer so far, I would say, is we have no idea. The derivation is by algebra. And it's, as I said, it's not intuitive, and you'll sort of, in my talk and Daniel Remenick's talk, you'll probably get the idea of how this is done. The KP equation is classically something you get from shallow water waves. And if you look at the regimes in which those things are derived, it appears to have no connection whatsoever to what we're getting. Of course, the KP equation does have all the scaling invariants that we are supposed to get at this scale. So the whole thing has to be, because it's a 1, 2, 3 scaling limit, it has to be 1, 2, 3 scaling invariant. And the KP and KdV equations do have that scaling invariance. And perhaps because we're looking at a universal fixed point, one shouldn't be so surprised to see some integrability, but there's a deeper question here, which is why the endpoint distributions should satisfy a closed equation at all. In general, one would expect that if you tried to write an equation for endpoint distribution functions, it would involve all the other endpoint distributions for other n, or at least perhaps for any n+1 or n-1 or something like that. And usually you get a hierarchy of equations. But here the thing closes in each n, which is very strange. If people are familiar with this field, they've heard that for flat or step initial conditions, one gets, for the one-point distribution, the Tracy-Whittem distributions, and I'll show you in the next slide that these things just fall out immediately from such a picture. So let me describe that. So we now know what the source of the Tracy-Whittem distributions is. So you get the Tracy-Whittem GUE distribution if you start with a narrow wedge, and the GOE distribution if you start with a flat interface in these universal random growth processes. Now these distributions are classically written two ways, either as Fredholm determinants or in terms of this integrable ODE called Painlevé-2. So let me use this Painlevé-2 because that's the natural thing here. So the Painlevé-2 equation is here. It's just this little ODE Q double prime equals RQ plus 2Q cubed. And RQ is actually a special solution of this Painlevé-2. There's certain boundary condition at infinity that it looks like an Airy function, and that's called the Hastings-MacLeod solution of Painlevé-2. So the GUE distribution is just e to the minus this funny integral of q squared, where q is this Hastings-MacLeod solution. And the GOE distribution is written in terms of, well, usually it's written like this: the square root of the GUE distribution times e to the minus this first integral of the Painlevé-2. Okay, now we know from our theorem, which I haven't shown you the proof yet, but if you believe it, that this phi, which is the second log derivative of the distribution function, should satisfy in the GUE case, KP, and in the GOE case, because it's doesn't depend on X, the KP reduces to the KdV equation. And you basically know what the narrow wedge initial data should look like. It should just look like a upside down parabola, x squared over t. So it's an expanding parabola going down, and with fluctuations of size t to the 1/3. So you could just guess as an ansatz that phi must have the scaling form t to the minus 2/3 of some psi of t to the minus 1/3 r plus x squared over t. Plug that into the KP equation, and you just get this nice little ODE out. And of course, if you just guess minus q squared, turns out to be the solution of this ODE as long as q satisfies Pavlov-A2. And for flat initial data, you have the same sort of thing, just a kind of natural guess for the scaling relation turns KdV into a similar looking ODE, which has solution psi equals a half q prime minus q squared. And all these integrals are just first and second derivatives upstairs. So this just tells you that the GUE and GOE distribution are nothing but special self-similar solutions of this KP equation looked at time 1. Okay, so that's where they came from. Okay, so so now for the rest of the talk, I want to try to describe how one gets all this. Okay, so so the first step, which you'll hear from Daniel Remenick tomorrow, is to solve a special discretization of the KPZ equation called TASAP. And its transition probabilities are given by certain Fredholm determinants. And there's a recipe to translate the initial data into an operator K. And then the determinant of that gives you the n-dimensional distributions of the TASAP transition probabilities. Now, TASAP is a model in this KPZ universality class. And so if we take this 1, 2, 3 scaling limit of TASAP, whatever we get should be the universal fixed point. Of course, the universality is still a widely open problem. So we take the 1, 2, 3 scaling limit of the TASAP transition probabilities, and we get objects which we can prove are transition probabilities. And the Markov process defined by those is the candidate for the universal fixed point in the universality class. It's a Markov process with explicit determinantal transition probabilities. So just a few technical things. The Fredholm determinant of an operator is a continuous map on the trace class. So it's important that these operators K, which I'll describe in a minute, are trace class. And the trace norm you can just think of as the sum of the absolute values of the eigenvalues. Unfortunately, the trace norm is a nightmare to compute. So that gives you this universal scaling invariant Markov process with determinantal transition probabilities, but there's still the question of where the partial differential equations come from. So we follow the route of Tracy-Whittam. You differentiate the determinants. So the log of a determinant is just asking to be differentiated because the derivative of a log of determinant is just a trace. So you differentiate the log of the determinant and you get a trace. And now you differentiate that trace and all the other variables, and you get big strings of operators, of traces of operators, and show that they satisfy some partial differential equation. So that's the route to get the results. Amazingly, if you try the same thing for the KPZ equation, so for the KPZ equation, it's known that for a couple of very special initial datas, narrow wedge, half Brownian, for example, the little object I have written here, this double exponential of the height function, it's called the Gumbel transform of the height function. So this expectation of e to the minus e to the h is remarkably computable in a few special cases. And again, you get Fredholm determinants. So you might want to take the derivative, the log derivatives of that thing. And in fact, they also satisfy KP. Again, completely unexplained. But even worse, it's not general. It only works for some, but not other of the special solutions for the KPZ equation. So keep in mind that the KPZ equation, the solvability is only for 1-point distributions for a few very special initial data. And so far, some of them work for this KP and others don't. And that's a big mystery that needs to be solved. Of course, this flat, the formula is a physics formula. It's conjectural formula. So it's plausible that there's things in the formula which aren't quite right. Okay, so let me just show you a big general picture, abstract picture to put all this in. We have a universe of models. It's an unbelievably high dimensional space. And in this universe are supposed to be all the type of KPZ class models. Many of them are Markov processes of evolving height functions, and others, there's like the original Eden model, there's not even a height function, but one can kind of dream that there's something like a height function. They're not all Markov. And in this universe, there's actually 2 universal fixed points, but the scaling for the 2 universal fixed points is different. So the type of scaling we're interested in is this 1, 2, 3 scaling here. That's what we're talking about. And under that 1, 2, 3 scaling, it's believed, or you could think about it as a definition, that all the models in this universality class converge to a universal fixed point, this KPZ fixed point, which is itself a Markov process, which I'm going to describe its transition probabilities in a minute. But there's another fixed point, which is the Gaussian fixed point, the Edward Wilkinson fixed point, which is a bit more trivial and is not surprisingly then better understood. And between these 2 fixed points runs a special heteroclinic orbit called the KPZ equation here in the middle. The KPZ equation has a coupling constant lambda, where if you send lambda to 0, then you just get a linear stochastic PDE, which you can solve in a few minutes. And that is what the physicists call the Edwards-Wilkinson model. And as lambda goes to infinity, which is effectively what you have under these 1, 2, 3 rescaling, of course, then you have to rescale it to make lambda finite and the small parameters in front of the dx squared h and the white noise. This KPZ equation will converge to this KPZ fixed point, as I'll describe in a minute. The 2 fixed points beside having different rescaling, so the scale invariance of the Edwards-Wilkinson model is down here. It's got a 1, 2, 4 scaling. So it's invariant under that. And also the two models have different invariances. So the Gaussian fixed point is invariant either if you change the height to minus the height, you get the statistically the same thing, or if you change time to minus time. So if you run the stochastic heat equation backwards, you can't tell the difference from the forward time. The KPZ fixed point is different. You have to rescale, not rescale. You have to flip time with the height function. You have to do both at the same time to preserve the invariance. It's skew time reversal invariant. So you have to do both at the same time to not be able to see the difference. Okay, and then we have all these models like the ballistic aggregate and the Eden model, which are conjecturally supposed to be in this class. Or if you like, you could take the easy model and you could put all pluses above an interface and all minuses below it. And then you could set a magnetic field. So the one of the two, let's say the minuses are preferred, and the interface would grow because of the magnetic field. And the more stable phase would invade the unstable phase. And the fluctuations should be given by this KPZ fixed point. If you didn't have a magnetic field, then the two phases of the Ising model are in balance, and the interface just fluctuates back and forth. And so it should not go to the KPZ fixed point because effectively the lambda is 0. And under the 1, 2, 4 scaling, this thing should be sucked into the Edwards-Wilkinson fixed point. Now, that kind of thing is provable because we understand these linear stochastic PDEs. And this little wedge at the bottom here, this little height, is supposed to tell you that we understand a little bit analytically above the level of the Edwards-Wilkinson fixed point. So this is sort of Martin Hare's theory or Gubinelli's theories about stochastic PDEs tell you that for some fixed positive time, one can understand the KPZ equation. There's a sort of little area above the Gaussian case, which one can understand. So for example, if you took the asymmetric exclusion process and you did a weak asymmetry, you take these weakly asymmetric scaled models, then under this weakly asymmetric rescaling, they converge to the KPZ equation in there. But this is all staying within the area in which one understands that KPZ is well posed and one understands what it means. So this little pink wedge is the analytically understood region. Now, what we're doing is we're taking a model like TASAP, or one of its friends, perhaps, push TASAP, discrete time TASAP. These things are also doable. And one has very little analytic understanding, but in this regime, but one can get exact formulas for these special models, and then rescale those formulas to get exact formulas for the KPZ fixed point. So this isn't being done in a kind of analytic way, it's being done in an algebraic way. Okay, there's no questions, I'll just...
Jeremy, could you try wrapping up in, say, 1 or 2 minutes?
Oh, really?
Over time.
Okay, sorry, my timer is off. Okay.
Yeah, please.
Let me just say what the fixed point transition probabilities are, and I'll stop.
Okay.
Okay.
Thanks.
Okay. So then the punchline is here are the exact transition probabilities of the KPZ fixed point. So the finite dimensional distribution. So if you start with some some function h0, and now you'd like to know what the finite dimensional distributions are at some time t later. That's all the information you need to describe this stochastic process for a fixed time, okay, or the transition probabilities. Just like with Brownian motion, it's defined in terms of its finite dimensional distributions. So these things are given by a Fredholm determinant on an m-fold product of L2. And so what I have to explain to you is the recipe, given the time and the x's and the a's, how to get from the initial data into an operator k, which is the thing which gives you the transition probabilities. Okay, so that's called the Brownian scattering transform. And you can see that this k, so this is the ijth entry of k. It's an m by m matrix operator. And its ijth entry is actually a kind of trivial evolution of a kind of base operator kh0, which is the Brownian scattering transform of the h0. And it's this, what I call trivial evolution, which once one takes the determinant and does the differentiation, gives you these nonlinear PDEs, the KP equations. So the only thing I have to tell you is what's this Brownian scattering transform kh0, and then I'll stop. So you take your h0, that's your height function h0, and what you do is you run a Brownian bridge from u1 at time minus L to u2 at time L. And you ask, what's the probability that the Brownian motion in between hits the hypergraph of your initial function h0? You have to phrase it like this, because some of our functions h0 are very strange functions. Like, for example, h0 could be this function and minus infinity everywhere else. It's just has one value at one point. So you have to talk about hypergraphs. That's called the narrow wedge initial data. I didn't draw it beautifully, but anyway, so you take this probability of hitting. It depends on L and U1 and U2, and you think of it as an operator in U1 and U2. And in fact, that operator already, from that, you can reconstruct the function h0 between minus L and L. Now you'd like to take L to infinity. As you do, it's kind of clear you can't reconstruct if you just took the limit of the operator L. But what this thing tells you to do is to solve the heat equation backwards, to refocus this P hit around the center, and then take a limit. This doesn't make exact sense, but as long as T is non-zero, the e to the td cubed smooths the thing out enough that the entire object makes perfect sense in the limit. And that's your Brownian scattering transform of your initial h0. You plug it into the Fredholm determinant, and that gives you your transition probabilities. And then log differentiating this determinant gives you these KP equations. And sorry, Nicholas, I'll stop.
Okay, so Carlo, please continue.
Thank you very much. So just thank you also, Nicola. So I also for the nice topic. So now I invite Tal to charge his comments on this talk, and after just Tal. So just to maybe to be practical, I will just when there are like maybe you have less time, I can give you 10 minutes, and when there are like 1 minute or 2 minutes left, I will switch on my video so that you will see my face, and you mean that you have 1 or 2 minutes. So that okay. I will not have. I will not have to stop you in the meanwhile. Is that okay?
Yeah, sure.
Okay, good.
Yeah. Now I cannot share my screen.
Yeah. Okay. So
okay. Perfect.
Okay. Now. Okay. Can you? Okay. Let's see.
Okay. Do you see my screen?
Okay. Good. Please go on.
Okay. All right. So thanks a lot for this talk, Jeremy, and thank you for staying for the discussion. And now I want to comment about Jeremy's talk from the point of view of time correlations. Well, let me explain. So first, I want to briefly tell you what we do understand, as Jeremy just showed us the nice picture with the two fixed points. So let me start with the easy case. The easy case is the Edwards-Wilkinson universality class and fixed point, and this one has the equation. This equation here, so this is the stochastic equation with additive noise, or the Edwards-Wilkinson equation. And this is an integrable system, Gaussian. It is Gaussian, the fluctuations are Gaussian. It satisfies the 1, 2, 4 scaling invariance. In other words, it is a fixed point of its own in its own class. So this is the terminology that we use here. But to give you some other models in this class, so for example, Jeremy mentioned a few, and I will repeat on some of them. So first one is the semi-discrete Edwards-Wilkinson. Okay, so you can think about this as a system of stochastic differential equation, where here you take the discrete Laplacian, and here these are independent Brownian motions in space. More generally, you can consider Ginzburg-Landau models, where instead of the Laplacian, you are taking divergence of a derivative acting on a gradient, okay, and of a convex function. And if this function is x squared, then we are exactly in this case, and otherwise it's more general. And you can take the simple symmetric exclusion. The high fluctuations, they obey more or less this equation. Okay, and the other class is the KPZ fixed point, I mentioned one, so we have no equation. However, it is a Markov process with now explicit transition kernel. We just saw them. So this is resolved by Matetsky, Quastel, and Remenick. And for quite general initial conditions. And here we have the 1, 2, 3 scaling invariance. And as Jeremy explained, then the best construction is probably the TASA, because you can actually compute things. And so this is a certain equation, semi continuous equation for TASA, if you think about it as in terms of high function, but I don't have time to explain. But anyway, so the 1, 2, 3 scaling is exactly this one. And what they proved in that paper is that this converges to the KPZ fixed point, and from there you can actually compute transition probabilities, all finite dimensional distributions. Okay, other models in this class that are provable are the last passage calculation. Okay, this is I found recently the PhD thesis of Alessandra Ocelli, and I think it's a great reference for that. Results before, but it's very well written. More recently, and in fact, I noticed that it was the same month last year. There was a result by Jeremy Quastel and Zarkar, and also Bombali Viraj, who proved that the KPZ equation is in the fixed point class, is in the KPZ universality class. Namely, that if you take the 3 to 1 scale, 1 to 3 scaling, it converges to the KPZ fixed point. They also proved in this paper that finite range type of face-up, and in the other paper, O'Connell-Yeo polynomial model. So this is the KPZ equation. I should not repeat that. And now regarding time correlation. So I see a question in the chat, but okay, I will get to that later. So yeah, so probably the first rigorous result on time correlation is due to Ferrari and Ocelli in 19, where they took the last passage calculation model with generic initial conditions, and they proved the convergence of the time covariances under the KPZ fixed point scaling, okay, to a certain covariances of some stuff that is written in variational formulas using Airy functions. Well, we now know that this is exactly the covariances of in terms of the KPZ fixed point. And in particular, they managed to get an explicit aging function in the stationary case. And I will explain very soon what do I mean by that for different models. So my talk is based on a joint work with Jean-Dominique Deuschel and Gregorio Moreno-Flores, where we considered these models in the stationary regime only. And what is nice about the stationary regime is that you can reduce yourself to understanding of the 1 point function. Okay, so I don't have a lot of time to explain it. I just want to mention, this is also related to Quastel's talk from before, that what is nice about these models, as Jeremy mentioned, that they are invariant under two-sided Brownian motion, but they are not in equilibrium. So by stationarity, we mean that essentially the gradient or the differences, these are stationary. Okay, or if you want the two-sided Brownian motion is invariant, but you don't know what is the value at 0. Okay, and there are correlations in time. And yeah, so Funaki and Quastel proved that the Brownian motion is indeed invariant for the Kohl-Opt solution of the KPZ. And you can get more, you can get that you have a space-time stationarity. Okay, so the whole process, the whole future of the process, if you shift it in space and time, is stationary. And this is very useful if you want to prove correlation, if you want to compute correlation. So let me try to explain that. So you can then, if you want to compute the covariance of your process in time t and position x and future time at and position d times x, then you can write it down as 1/2 the variance of the first plus the variance of the second minus the variance of the process evaluated on the increments. And yeah, the reason is that the increments are equal in law to the process evaluated on the space-time increment. That's the point. And when you have that and you want to compute the correlations of the process, then you can write them down only in terms of variances. And this is nice because if you know how the variance will scale, then you know how to take the limit. So with Dominique and Gregorio, we computed for Ginzburg-Landau, the Ginzburg-Landau model, the variances. It was known, I mean, the scaling limit was known, but we found this nice presentation of the variance in terms of modulus of a Brownian motion or a simple random walk, or more generally for Ginzburg-Landau for a certain random walk in dynamic random environment. And if you have a CLT for these guys, then you can get your limit for the variances. Okay, very, very explicitly. And there is a result by Corwin and Gauchal from 20 that KPZ equation, the Kohl-Opt solution, general initial condition, the variances converge with the Rightly scale. So adding these two facts together, what you get is that in the stationary case, if you fix an A larger or equal than 1, and in the KPZ equation case, you take x and y to be rule O of t to the 2/3, then the correlations of these two space time points, okay, so you compare time t and time A times t, they converge as time t goes to infinity to this explicit function It's called the aging function of the KPZ. And in the Ginzburg-Landau or the Wilkinson, if you take x and y to be little of t to the 2 to the 1/2, you get that these correlations converge to this aging function. And you see here the scaling here of the KPZ and here of the Edward Wilkinson. Okay. And in the Ginzburg-Landau, we can, because of what I just mentioned, we can actually take x and y to be of order t to the 1/2. And it's trivial for the KPZ fixed point itself and for the Edwards-Wilkinson equation itself. It's just translation invariance. But the question is if you can prove that for example, for the KPZ equation. Okay, space-time correlation, the limit of space-time correlation. So this is one interesting question. Maybe someone can answer me even now on this question if this is no. Another point that I want to make, another question that I want to ask, and this is my last slide, Carla. So so we proved that with Jean-Dominique and Gregorio, that if you take the O'Connell-Lior model in the intermediate regime, then the correlations and actually all moments of the log converge to the ones of the KPZ equation. So if you first take n to infinity and then time to infinity with the right comparison as I presented here, then you have aging. The question is, can you do that for fixed n, fixed but large n? And you get aging for already the O'Connell-Lior model. And you can ask the same question for long-range data, for example. Okay, and there are available results in this direction for the KPZ equation in Corin, Goshal, and Ammons, and also in Ferrari of Che. Okay, this is all I wanted to say. Thank you.
Thank you very much, Tal. So now I just we do not have so much time. I just check it. So like I just give you the possibility. So there was in the chat. So there are also the question from Tal, and there is also in the chat a question from Jonathan Mattingly talking about the symmetries which cause those terms to be the remaining terms, and I give the possibility to Jeremy if he wants to reply, and after we move to the next talk.
I'm happy to reply, but I don't see the question.
No, okay, there are the question of Tal at the end, and also there is in the chat there is a question from Jonathan. Maybe.
I can just ask the question. Maybe that's easier. Jeremy,
You can also ask the question.
Yeah,
you said, you know, why it was quarter vector Vries, why it was quarter vector Vries with the fourth order with the biharmonic term regularizing it. I mean, if I remember those derivations in the physics literature, they come from symmetries, right? That you can impose on the problem when you kind of do a small h expansion. Can you comment on that a little bit from the point of view of what you know and know and know and know? Right.
Okay, I'll say one thing. As I said, the big surprise is that there's an equation. If you believe there's an equation, and now you start imposing symmetries, it's not that hard after the fact to say it must be these.
Okay. It's a very, very nice and efficient answer to your question. So now, but okay, of course, let me check if there are yet some questions. Okay, I think that we are done. So I will thank both Jeremy and Tal for this nice discussion.
So there's actually another question in the chat.
Right, I didn't see. Okay, sorry. It's
There's another question.
from where? It's in the chat.
By Zhen Jiao's son. So he asked if H satisfies some SPD. So I guess it's sort of the same question. Probably.
No, that's a different question. Someone just asking if H satisfies the SPDE.
Yeah.
Is that the question?
Yeah.
Okay, sorry, it's hard for me to read the chat the way I've opened up the window. Yeah, so H does in the fixed point, it actually does not satisfy an SPDE, at least as far as we know. I don't imagine it does. There's an analog which is a variational problem involving an unknown noise called the Airy sheet. And you know, if you like, you could send me an email, whoever's asking the question. I could show you it was in one of my later slides.
Okay, so sorry because I didn't see. Thank you very much, Nicholas, also for catching the question around.
Right, and then there is also a question from Li Cheng Tsai about DASEP or a comment. So maybe you can comment on this.
Yeah, so it's not. I said that it's morally the same as the semi-discrete equation, but okay, there are some dependencies. But it's morally the same.
Okay.